We're moving on from yesterday. We talked about mass, molar mass, and we talked about molecular mass, right? Talked about this idea of an AMU. And today we're moving on to the concept of the chemistry mole. Cannot not do this. This is a chemistry mole, okay? That just so we have this visual image of a mole in his lab coat with goggles holding a tetrahedral, which has bond angles of 109.5 between all the bonds, right? So that could be like a CH4 or something like that. But the idea here is if we think about a mole, and a mole is not a creature, well, this is the way most of us remember it. It's a mole. But remember that a mole is actually a unit of count. It has to do with Avogadro's number. We'll talk about later about, we may go into some more detail about how Avogadro, which is a person's name, his last name is Avogadro. His first name is long, too, and I believe it's Spanish, and so it's really difficult for me to say. His last name is Avogadro. And Avogadro came up with this number of 6.02 times 10 to the 23rd. As he was doing his experiments, he kept coming up with this constant. This number keeps showing up. And in science and math, when something keeps recurring, it keeps coming up over and over and over again, there must be some significance to it. Now, as you said before, and we've already covered this, that a mole, this is kind of a preview, that a mole is actually a unit of counting. Whereas before we may have said something like, give me 1, then you would give me a single, right? If I say give me a pair, you would give me 2. If I said give me a dozen, you would give me 12. Unless I ask you for a baker's dozen, which is 13, right? Because we always get one more. Okay. So a baker's dozen with 13. I said a score would be 20. Okay? And a mole would be 6.02 times 10 to the 23rd of them. A mole is nothing more than a unit of counting. If you get confused about what a mole is, think of it and say, oh, it's like a dozen. A dozen is 12. A mole is 6.02 times 10 to the 23rd of them, of that thing. If I said I need a mole of students, yeah, that's a lot of people to feed, right? Bring your own lunch, okay? If I need a mole of pencils, if I need a mole of whatever it is, a mole of them would be this many. This many. That's a lot, right? That is a very, very large number. And so we tend not to get a mole of things that have any real volume. When we talk about moles of things, in order for us to even be able to comprehend it, sometimes it's got to be very, very, very small. As a matter of fact, just one way for you to think about this, try to relate a mole to something that you can see. We've talked about a mole being a large number of them, but when they're very, very small, it takes up a reasonable amount of space. Let's talk about something that you can kind of comprehend, and that would be a marble. One of the videos we may watch talks about getting a mole of marbles. 1 mole of marbles. Everybody has an idea what a marble's like. Little sphere about this big. 1 mole of them would cover the surface of the entire Earth 3 miles deep. That's how many we're talking about. 1 mole of marbles would cover the entire Earth to a depth of 3 miles. That's a huge number of marbles. So I want you to think, if you were the size of a marble, and you had all your peers all around you, right? When we talk about putting out a mole of sodium, for example, that there are as many sodium atoms in that mole of sodium as there would be marbles to cover the Earth to 3 miles deep. That is a huge number. It's 6.02 times 10 to the 23rd of them. So that's why we don't use, I need a couple atoms, I need a dozen atoms, I need a score of atoms. It's too small for anything we have precision-wise to measure out. But we can say, give me enough of them that if they were marbles, they'd cover the Earth 3 miles deep. That's a huge number of them. That's so big that when it comes to actual atoms or molecules, it's enough that I can actually measure on one of our triple beam balances. So some understandings you have to have is that 1 mole of an element is 6.02 times 10 to the 23rd atoms of that element. Give me a mole of sodium, it's going to be 6.02 times 10 to the 23rd moles of sodium atoms. And also, that 1 mole of a molecule is 6.02 times 10 to the 23rd molecules. Remember, it doesn't have to do simply with chemistry, though this is the only place I've really ever seen it used, that a mole is actually just a unit of counting. And so I say I need a mole of sodium, or I need a mole of sodium chloride. If I have a mole of sodium, it's going to be 6.02 times 10 to the 23rd atoms of sodium. If I say I need sodium chloride, give me a mole of sodium chloride, it's going to be 6.02 times 10 to the 23rd molecules of sodium chloride. Now, knowing that it's NaCl for the molecule of sodium chloride, that would mean that I would have 1 mole of sodium ions and 1 mole of chlorine ions that come together to form 1 mole of sodium chloride molecules. Everybody tracking so far? Makes sense. Okay, so here's kind of those applications in your book. This is one of the really neat things where we start to look at the periodic table, and here's some information that you can actually use. You can actually use the fact that 1 atomic mass unit, we did that yesterday talking about AMUs, right? We measure the mass of atoms and molecules in AMU. That 1 atomic mass in AMUs is equal to the mass of 1 atom of that element. We talked about carbon with an atomic mass number of 12. We said, okay, if I wanted to take the mass of 1 individual carbon atom, it would be 12 AMU. But also, here's where it gets usable to us. That 1 atomic mass in grams is equal to a mole of that element. So again, let's say we're considering carbon. Say we've got carbon 612, meaning that it has 6 protons, that it has a mass of 12, meaning it's got 6 protons and 6 neutrons to come up with carbon 12. That 1 carbon atom is equal to 12 AMUs, the mass of 1 atom. The mass of 1 atom is 12 AMUs because it has an atomic mass of 12. But the mass of 1 mole of carbon-12 is equal to 12 grams. See, I take the same exact number. If I can see that it's 12 AMU, then I know to have 1 mole of it, I need 12 grams of it. I use the same number, different units. So whereas 1 atom, 12 AMU, 1 mole of atoms, 6.02 times 10 to the 23rd carbons, is going to have a mass of 12 grams. And guess what? 12 grams is well within our ability, well within the precision of our triple beam balance over here. So if we had a sample of carbon, we could take a triple beam balance, we could set it for 12 grams, and we could slowly shake off carbon onto the surface here until it balanced at 12 grams. And when we had 12 grams of carbon, how many atoms of carbon do we know we have? We know we have 6.02 times 10 to the 23rd atoms of carbon, because 1 mole of carbon has a mass of 12 grams. Okay? This is where it actually becomes usable to us. We can't get the mass or figure the mass of one, or can't use it really, but we can figure the mass of this many of them, and we can then use that in calculations. We can actually weigh that in the lab because we have so many of them. 6.02 times 10 to the 23rd carbon atoms has a mass of 12 grams. In the same way, we talked about the molecules. That one molecular mass in AMUs is equal to the mass of one molecule of the compound. Okay? The mass of one of them. So, for sodium chloride, let's use that as an example again. If I wanted to know what is the atomic mass, or the molecular mass actually, of the molecule, what is the mass of a sodium chloride molecule? How would I determine the molecular mass of sodium chloride? Okay? So I've got sodium chloride. I want to know, sometimes abbreviated MM, the molecular mass of sodium chloride. How would I determine that mass? The mass of a sodium chloride molecule. Right, so it would be the mass of sodium plus the mass of a chlorine. So what's the mass of a sodium atom? 23. Mass sodium from the book, 23.0. Okay, 23.0 what? One atom is 23.0 AMUs. Good. And chlorine. The mass of one chlorine atom is 35.5 AMU. So the mass of one sodium chloride molecule is the sum of these two, which would be 58.5 AMU, meaning the mass of one individual molecule of sodium chloride, it has a mass of 58.5 AMU. But here's where it becomes usable to us. What is the mass of 1 mole of sodium chloride? In other words, 6.02 times 10 to the 23rd molecules of sodium chloride. What is the mass of that? Right. 1 mole of sodium chloride is 58.5 grams. We take the number of AMUs that we calculate and we change the units from AMU to gram. So if I asked you to go out and measure out 58.5 AMUs of something, you can't do that. We don't have anything with that precision. However, if I ask you to go over and measure out 58.5 grams of it, you can do that. Okay? Because we're not looking for one, we're looking for 6.02 times 10 to the 23rd of them. So down in here, the molecular mass in grams is equal to the mass of 1 mole of that molecule. So again, just in summary, Avogadro's number is a number. And 1 mole of anything is equal to Avogadro's number of that thing. 1 mole of sodium is 6.02 times 10 to the 23rd atoms of sodium. 1 mole of sodium chloride is 6.02 times 10 to the 23rd molecules of sodium chloride. Okay. Now I heard someone say they're so confused. Yeah. What's confusing? This? Okay. Do you understand the idea of finding the mass of a molecule by adding up the masses of the components? Yeah. Okay. So you understand then, you accept the fact that sodium chloride, that 1 molecule relates to 58.5 AMU. Right? Got that. So for the mole, all we're doing is saying, okay, I need something I can actually work with. I can't work with AMUs. I need a mass which is actually big enough that I can measure it out, that I can relate it to something. Because remember, when we do chemical equations and reactions, we're going to be doing in proportion. When I said, one of these and one of these reacts to produce one of these and one of these, for every 1 and 1, you make 1 and 1. It's a ratio. It's a proportion. We're going to find out soon is that not only can I relate 1 and 1 to make 1 and 1, but I can do 6.02 times 10 to the 23rd to 6.02 times 10 to the 23rd to produce 6.0 times 10 to the 23rd and 6.0 times 10 to the 23rd. It'll make more sense in a moment, but it's called stoichiometry. But this movement of relationships between the coefficients. I need 1 and 1 to make 1 and 1. Or I need 2 and 2 to make 2 and 2. Or I need 10 and 10 to make 10 and 10. Or I need 25 and 25 to make 25 and 25. Or I need 6.02 times 10 to the 23rd and 6.02 times 10 to the 23rd to produce 6.0 times 10 to the 23rd and 6.0 times 10 to the 23rd. It's just a big number, okay? But the proportions are going to be the same. All we do then, if we need to know the mass of a mole of it, is to take the mass of a molecule or an atom, depending upon what we're looking at. We're looking at elements, we're going to take an atom of it. If we're looking at molecules, we're going to look at, the whole molecule of it, a compound. We're looking at the molecule. And what is one whole mole of that worth? Figure out the mass of one molecule in AMUs, and 1 mole of molecules relates to the same number, but this time in grams. Just change the units. So you find the mass of 1, change the units from AMUs to grams, and now you know the mass of 6.02 times 10 to the 23rd of them. We're going to do a couple problems to show that. Yes, ma'am? It's because every element has a unique mass. It's basically, again, another relationship. Avogadro, in doing these experiments, came to realize that there was something going on, that the mass was being multiplied, being changed, and that the numbers were being multiplied. And the relationship kept coming back to this constant of 6.02 times 10 to the 23rd. Right now, I don't want you to struggle so much with why it's that number. I just want you to be able to use that number in calculation. So let's try that first, and let's do a couple calculations and see if it doesn't start to make sense. What we have here is this basic understanding then from the text and from what we've learned so far, that if I want to know how many I have of something, like how many atoms of this element do I have, or how many molecules of this compound do I have? To get the number of them, I take how many moles of that thing I have and multiply it by Avogadro's number. If I want to know how many I have in terms of a count, I take how many moles I have and I multiply it by Avogadro's number. Now you can see that this is from this equation we can solve for any one of these elements, right? Now that we know, or one of these components, one of these variables, we've got how many moles, and Avogadro's number. Avogadro's number is a constant. It's never going to be anything other than 6.02 times 10 to the 23rd. So if we have how many, or if we're looking for how many, we need to have moles to do the math. If I'm given how many, then I would divide that by Avogadro's number to determine how many moles I have. If I told you that I had 37 times 10 to the 23rd molecules of something, you could tell me how many moles I have by dividing that by Avogadro's number. So the way to learn it right now, if how many do you have, it's equal to the number of moles times Avogadro's number. And if you have that equation down, you can rearrange it to solve for the moles. And also that the moles of a sample, how many moles do I have, is equal to the mass of the sample divided by the molar mass or the molecular mass of whatever it is I'm looking at. So again, if we're looking at chlorine, it's 35 35.5 grams per, that would be just one chlorine. But what would chlorine normally occur as? Not as a chlorine atom, but as a chlorine molecule, and it would actually have a mass of 71, wouldn't it? 35.5 times 2 to be 71. Let's go through some problems applying this and see if it helps it click for you. Now, this concept of the mole, and this whole day today is just about the concept of a mole. We're actually going to spend 2 days after this applying the concept of the mole. But just to because we recognize that it's hard, it's one of those existential things that you got to just kind of wrap your head around the concept and accept it, okay? If I send you to the store to get me a dozen eggs, you hopefully come back with a container containing 12 of them. If I send you over to the lab side of the room and ask you to come back with 2 moles of carbon, I'd hope you'd be able to figure out the mass of 1 mole of carbon, double it, measure out that mass, and come back with that sample. It becomes important because we're going to actually use it later on when we do reactions, so we don't have any extra of anything. It's a perfect recipe, perfect reaction. In order to have the perfect reaction, we have to have the exact amount. In order to have the exact amount, which we would never have absolutely perfectly, but we can approximate really closely, we can't do that at the individual molecule and atom level. We have to do it at the Avogadro or the mole level. Let's look at this first one that's in your book as example 7.5. Actually, not 7.5. It's over on 260, I believe. No, yeah, 260, example 7.6. How many moles of fluorine exist in a 50-gram sample of fluorine? How many moles are in 50 grams? Or how many moles does 50 grams represent for fluorine? Well, if we use this basic relationship up here, that the moles is equal to the mass divided by the molar mass. Yes? Of 1 mole. Then what is the mass of 1 mole? Is the molar mass. What is the mass of 1 mole? We said before, what is the mass of 1 mole of carbon? What is the mass for 1 mole of carbon? What is the mass of 1 atom of carbon? How would we figure that out? 1 atom of carbon, we would flip to the periodic table in the front of the book, look at it. Oh, carbon has a mass of 12.0. The individual carbon atom has a mass of 12.0 AMU. 1 carbon atom has a mass of 12.0 AMU. So 1 mole of carbon has a mass of 12 grams. So the molar mass of carbon is 12 grams. Everything has its own molar mass. Everything is different. You know, if you have something that's very, very light, which means it has very little mass in it, 6.02 times 10 to the 23rd of them has a relatively small mass. If you have 1 atom that is huge and, you know, one of the higher numbers on the periodic table, that 1 atom is going to have a very large mass. And so 6.02 times 10 to the 23rd of them is going to have a very large mass relatively as well. So everything has its own unique mass. A mole of an element or a mole of compounds made up of those elements. You can imagine that if you have a compound up here that has huge numbers, like yesterday we did the Si6H12O6 molecule, you've got to add the masses of all those things together to figure out what the mass of 1 molecule would be in AMU, then change the units to grams and say 6.02 times 10 to the 23rd of them has the mass of so many grams. In this case, we're asked to find the moles of fluorine in a sample of 50 grams of fluorine. It's really just a straightforward math problem. The moles is equal to the mass of the sample. In this case, how many moles are in 50 grams? My sample is 50 grams. And the molar mass then is something that I need to compute, right? Or I need to figure out. What is the molar mass of fluorine? Again, I'm going to find that on the periodic table. So flipping to the periodic table, finding fluorine over on the right-hand side, column 7A, second row down. It has a mass number of 19. The mass of one fluorine atom is 19 AMUs. The molar mass, meaning the mass of a whole mole of that then, is equal to what? 19 grams. .0 grams. And therefore, how many moles do we have? Just by doing the math right there, it's going to end up to be 2.63. 2.63 moles of fluorine. Now, in the book, here's something, if you look at the book, when it walks through this, 19 grams of fluorine is equal to 1 mole of fluorine. That's our new unit conversion factor, right? 1 mole equals 19.0 grams. What they're talking about here is atomic fluorine. How does fluorine normally occur? Isn't it a homonuclear diatomic? So this is one place where I don't think it's clear enough for you. They should have said, you know, where it does say on the top, how many moles of fluorine atoms? Okay? If they had not told you that they're talking atoms, if they had said, how many moles of fluorine exist? That's a different question, isn't it? Moles of fluorine would talk about how does it naturally occur. It naturally occurs as a homonuclear diatomic. And so the mass of a fluorine would have been 2 times 19, or 38. But because they said how many moles of fluorine atoms, not fluorine molecules, then it's 19 grams. So the math there, the number of moles is 2.63 moles of fluorine. Let me ask you the question then. If we have 2.63 moles of fluorine, how many atoms of fluorine do we have? Okay. We have 2.63 moles. And I need to convert it into something that's going to give me atoms. I need some unit conversion factor that's going to relate, I got to get rid of moles, and I want to find atoms. I need some unit conversion factor that's going to relate the number of atoms to the number of moles. What might that be? Avogadro's number. Because I know with Avogadro's number that 1 mole of those atoms is equal to 6.02 times 10 to the 23rd of those atoms. Okay? Moles cancels moles, and I'm left with atoms. So my units are right. Then we would do the math. 2.63 times 6.02 times 10 to the 23rd. Somebody with a calculator, just do the coefficient. What is 2.63 times 6.02? This isn't in the book. We took this problem one step farther. Clearly? One more? 1.58? It would actually be 2 times 6 has got to be like at least 12, so it's probably 15 point, right? 2.63 times 6.02. Give me your numbers again. 15 point what? 83. 15.83. Now let's deal with the scientific notation. This is times 10 to the 1st times 10 to the 23rd. This would be then 15.83 times 10 to the 23rd. To put it in correct scientific notation, it would be 1.583 times 10 to the 24th. However, this is not exact It has 3 significant figures and 3 significant figures, so my answer would be 1.58 times 10 to the 24th atoms. 2.63 moles of fluorine is the same as saying 1.58 times 10 to the 24th atoms of fluorine. I computed the moles by knowing the mass and the molecular mass, or the molar mass, excuse me, to compute the number of moles. I took the number of moles and multiplied it by Avogadro's number to determine how many atoms of fluorine that is. Next question, next example, gives us the mass of sodium chloride and asks us to determine the number of moles of sodium chloride. So again, the moles is equal to the mass divided by the molar mass. The moles is equal to the mass divided by the molar mass. We're asked to find the moles. So in this case, we need the mass of the sodium chloride divided by the molar mass of sodium chloride. What is the molar mass of sodium chloride? Let's do it over here. The molar mass of sodium chloride, it's equal to the molar mass of sodium plus the molar mass of a single chlorine atom, right? We have 1 and 1. So what's the molar mass of sodium? 23, okay? 23.0. And of chlorine, a single chlorine? 35.5, right. We're going to have that one memorized. 35.5 and 23.0. For a molar mass of sodium chloride, the compound, as being 58.5 grams per mole. 58.5 grams per mole. The molar mass is 58.5 grams per mole. Why? Because 1 mole is 58.5 grams. So the number of moles is equal to the mass divided by the molar mass, which is equal to the mass of the sodium chloride we have divided by the molar mass of sodium chloride in all cases. In all cases, sodium chloride has a molar mass of 58.5 grams. So let's do the math over here. Our mass of our sample of sodium chloride is 5.000 grams divided by the molar mass of sodium chloride, which is 58.5 grams per mole. And the number of moles comes out to be right. The actual math is 0.0855. Let's start with the more detail. Work back, what should it be? Significant figures in the numerator is 4, right? Significant figures in the denominator is 3. Since we're doing division, our answer can only have as many significant figures as our least number of significant figures, right? So we're limited to 3. And that brings us to 0.086, I believe. Okay, that makes more sense. 0.0854. Okay, and that's how many moles of sodium chloride. Okay, that's how many moles of sodium chloride we have. Now the next thing to do is say, okay, I've got that many moles of sodium chloride. How many molecules of sodium chloride do I have? I would just simply take that number there and multiply it again by Avogadro's number. Every mole has 6.02 times 10 to the 23rd. So if I've got 0.085 moles, 0.085 times 6.02 times 10 to the 23rd will tell me how many moles of sodium chloride molecules I have. Hey, if I knew I had this many moles and every mole was worth a dozen, you would take this number and divide it by 12. Right? So, or excuse me, you take this number then and multiply it by 12, not divide by 12. You take the number of moles and multiply by 12. If a mole was 12, if it's the same as a dozen, if I said if I've got this many dozens, how many do I have? You'd take this number, multiply it by 12. Now I'm saying I've got this many moles. How many is that? Well, you've got 0.085 times this number, 6.02 times 10 to the 23rd, to give me the actual number of molecules of sodium chloride. Also notice here too in the units where I said moles is equal to grams divided by grams per mole. What's another way to write grams divided by grams per mole? It's the same thing as writing grams times what? When you divide by a fraction, is the same thing as multiplying by the reciprocal, right? We're going to invert this. So grams times moles per gram. Grams will cancel grams and leave you with moles. That's a quick check to see if your setup is right. Moles, in this case, moles equals moles. Yes, my setup is correct. We've got one more sample problem here in the book. Go ahead and clear this and we'll move on to that one. Thought we had one more. Oh, it was really just the application of what we just said. How many molecules of sodium chloride are in a 5-gram sample? We figured out how many moles at 0.085. Then it says how many molecules, multiply it by Avogadro's number. So the last part of the problem is just what I talked through at the end there. Let's go ahead on your own. 7.7 for those of you in 3rd edition. I'll read it for you in a second. Start working it, and then I will do it on the board. It says, how many moles of scandium atoms are in a 50-gram sample of scandium? Scandium. Okay. I'll get our periodic table on the board here. Scandium. Where are we going to find that at? It probably, let's assume it starts with an S, right? Transitional metal. Okay. Yeah, that blur right there looks like scandium. Hey, with my bad eyes, with these bifocals, I wonder if I take it off, it'll... No, it's not any clear without them. You always wonder, hey, does blurry plus blurry equals clear? No, it doesn't. Blurry plus blurry makes blurrier. So scandium right here. It's where it's at in your periodic table. If I look at the front here, now that I've found it, it says scandium is, let's use 45.0. It has a 45.0 and its atomic number is 21. Okay? And so the question is, how many moles of scandium, how many moles are in a 50-gram sample of scandium? So the mass of scandium we're looking at is 50.0 grams. our basic setup. Want to solve for moles. Moles is equal to mass divided by molar mass. Okay? The number of moles is equal to the mass we have divided by the mass per mole for that element, whatever it is. So in this case, the moles of scandium is equal to the mass of the scandium we're talking about divided by the molar mass of the scandium, okay? This is what we're looking for. Over here on our calculation, what do we have? We've been given the mass to look for, right? We've been told we have 50 grams. The question we need to know is, what is the molar mass of scandium? What's the molar mass of scandium? Because if we have the molar mass of scandium, we'll take the mass of the sample we have, divide it by the molar mass, and that'll tell us how many moles of scandium we have in our hand, right? Molar mass is in grams. So what is the molar mass of scandium? That's the only thing we lack, right? The molar mass of scandium. We look at scandium, and we see that scandium has a atomic mass of 45.0 AMU. So every atom of scandium has a mass of 45.0 atomic mass units. But now we've learned that we can take that same coefficient, that 45.0, and say, well, that's the molar mass, 45.0, change the units from AMUs to grams. And when I use grams, that is for every mole of scandium. So this number right here becomes my molar mass by changing it from AMUs to grams. So I've got 50 grams of scandium. I'm dividing it by 45.0 grams per mole of scandium. And what's the math come out to be? What's 1.1? 1.1 moles of scandium. I have 1.1 moles of scandium when I have a 50-gram sample of scandium, because I know for every 45 grams of scandium I have a mole, and I've got a little bit more than 1 mole. I'll go with a 1.1 moles of scandium. Now I say, okay, I've got 1.1 moles of scandium. How many atoms of scandium do I have? Well, my number of atoms, which is also number of molecules, right, if I'm talking about a molecule, but in this case I'm talking about an element, so I'm talking about the number of atoms. The number of atoms is equal to the number of moles times Avogadro's number. So if I've got 1.1 moles times 6.02 times 10 to the 23rd atoms per mole, I'm going to have about 6.6 times 10 to the 23rd atoms of scandium. 6.6 times 10 to the 23rd atoms of scandium, because I have 1.1 moles of scandium, because I have 50 grams of scandium and 45 grams per mole of scandium. This becomes significant because we said before, when we do equations, when we do reaction equations and we balance it, we know that when we say I take 2 and 4, well, if I can't measure 2 and 4, maybe I can measure 2 times 6 times 10 to the 23rd, and 4 times 6 times 0, 2 times 10 to the 23rd, and actually produce this reaction. We'll pick it up tomorrow.